Hi guys, in this video we'll be looking at mass spectrometry. Notice that it is spectrometry and not spectroscopy. Spectroscopy is where you use some type of light or some type of electromagnetic radiation such as IR or UV vis or even X-ray. In mass spec we do not use light, and so it's more appropriately just to call it mass spectrometry. We do produce a spectrum. Now this is typically shortened to just mass spec. Now this opening page shows an application of mass spec towards medicine, towards the analysis of potentially cancerous tissue. This shows where the instrumentation has been taken into the so-called clinic and been more broadly useful towards medicine. Once we go through mass spec, you can then look back at this and hopefully it will then be more relevant. Note that mass spec can even be shortened to just MS, typically. So in this example, they have taken mass spec and they have put it on wheels, and so they can roll it into the clinic or etc. Interesting application. Okay. Let's start by looking at IRs. And we really want to point out the limitation of IRs. Take a look at these two alcohols. Very similar structure. Can you assign each alcohol to its mass spec? Which mass spec, I'm sorry, not mass spec, which IR belongs to which alcohol? It's actually nearly impossible to tell. Both of the IRs show an OH. Both of the IRs show just below 3000 sp3ch, correct? And then of course both IRs show a fingerprint. Very similar. The fingerprints are of course different because it's two different compounds. But which is which? Again, nearly impossible to tell. If we had some known IR, like if we took these two compounds and we ran an IR of each of them, well then that would give you your answer. Or if we could find a known IR for one of these and say, okay, which one does it match, then we can use fingerprint to match it up. But as is, it's very impossible to tell, and this shows a limitation of IR. Both IRs show some functionality here, but we cannot assign each IR to each compound. Now, on the other hand, if we look at the mass specs, these are the mass specs of each compound. One of them is called 1-propanol. Here's the structure here, and the other is 2-butanol, 4 carbons total. Now this is sort of, we'll eventually learn how to interpret these, but this is just to show you the mass specs here at the beginning. Importantly, some important things. The x-axis. This is going to be, usually it's written here, but this is your M to Z ratios. Okay? This is essentially your molecular weights. This is mass to charge ratio. If the charge is 1, which it typically will be, thus this is typically just mass. So the x-axis, these so-called peaks or lines, I'll usually call them peaks, these peaks are going to correspond to mass. For example, right here we have something that's registering as a mass of 60. Well, that's actually your molecular ion. If we look at this molecule, the molecular weight C3HO equals 60. Okay. Now that is just a nominal mass, whole number mass. We're not going to be doing any decimal places when we do low resolution mass spec, standard mass spec. Now near the end we will look at high resolution mass spec, and that's where we will consider the molecular weight out to 4 decimal places. But most of everything we'll be doing will be low res, nominal mass, and the mass of this is 60. And indeed, we're seeing a peak at 60 that corresponds to the mass of this molecule. Where below, this alcohol has a mass of 74. Now actually in this example, the so-called molecular ion, which we will call M+, is nearly absent. It basically is absent, but at 74, we expect to peak at 74, it's basically absent. That's a bit unfortunate for this early example, but it is something that we need to be aware of and may see along the way. Okay, the other peaks that we see here are going to be fragments that come from the original molecule. So the original molecule is 60, but when it starts breaking apart in the mass spec, and we'll talk about this, it forms lower molecular weight fragments, and these also show up. Okay, the tallest peak in your mass spec is called your base peak. And the base peak here is m to z equals 31. Where the base peak below is 45. And once we learn more about how to predict cleavage in mass spec, these base peaks will really help us know which alcohol goes with which mass spectrum. Now I've already assigned it. I'm telling you that this mass spec is this alcohol. But in the future we'll be able to know that on our own, or at least should. Okay, the y-axis is basically just relative intensity. The base peak is always set to 100. There's really no units here. That's just like 100%. We just set it to 100, and everything else is in relative to that. And then we can just basically say that the peak that's occurring at 27 has a relative intensity of about 10. So it's about 10% the height of the base peak. Okay. Note that when we add up the molecular weights, nominal masses, whole number masses, carbon is 12, hydrogen is 1, oxygen is 16. Add these up and that's how we get our 60. We're using the major isotopes, carbon 12, hydrogen 1, oxygen 16. We will talk about when we want to consider the other isotopes. Okay, so on the next page we'll look at basically the instrument and talk about how do we get peaks in the mass spec. Okay, we begin with some type of molecule. First thing we have to do is we have to ionize this molecule. Ionization, converting it to an ion. We convert it to a cation. And the way we do this is, well, there's actually a variety of ways that we can ionize. The most common method of ionization is electron impact. That is, we bombard the molecule with an electron beam, essentially electricity. Electrons come in, they hit the molecule, and that causes an electron from the molecule to be ejected. I'm showing that 2 different ways here. 1 electron in, 2 out. One was the original, the other came from the molecule. Or we can show it like this. That is, the ionization converted this to an ion and we ejected the electron. So we lost an electron. We formed the ion plus the electron. Okay, since we lost an electron, the charge of the molecule is now positive, so it's a cation. But it's also a radical, because if you think about it over here, all of the electrons in a typical molecule are paired. They're either bonding pairs or lone pairs. And if you lose one electron, you'll have one electron remaining that is unpaired. That makes the molecule a radical. We show that by just showing one dot as an electron. This indicates that we have an unpaired electron in the molecule. We also show the charge. Again, being positive because we lost an electron. So, ionization forms a radical cation. Both radical and cation. The radical cation is also called our molecular ion, because it's essentially the ion of our molecule. We have not lost any atoms. Since we only lost an electron which has nearly negligible mass, the mass here is the same as the mass here, especially if you're just looking at whole number masses. So, molecular ion. Now, the molecular ion may show up in the mass spec, but it will also certainly fragment. This radical is a high energy species. It will fragment largely driven by entropy. Fragmentation can be very predictable, and we will learn how to predict this. For now, though, it's important to know that when a molecular ion fragments, it will fragment into cations and radicals. That is, the radical cation will break apart and form a radical and a cation. Now, the cation is charged. That's why we call it a cation. Important to know is only charged fragments will show up in your mass spectrum. So these show up some type of mass. It's going to be less than the molecular mass or the molecular ion because it's a fragment. The molecular ion can show up because, again, it's an ion. The radicals are typically not going to show up because typically they will be neutral. Of course, there can be exceptions. Some radicals can be cations. Our original was a radical cation. In general, though, these will show up, these will not. Okay, let's look underneath the hood of the instrument. All this is in a box. If you look at an instrument, you will see just sort of a port where you inject your sample. We typically inject a solution, so your molecule is dissolved in some type of solvent. And we use a syringe. We inject into the sample port. The sample goes into basically the ionization chamber, where it encounters the electron beam, and ionization takes place. The resulting radical cations are directed towards a magnet. This is done because we have some negatively charged plates which pull the positively charged cations in this direction towards the magnet. Other species, such as potentially anions or neutral molecules, are not pulled towards the magnet. This is why only cations show up in the mass spec. There's also a vacuum pump here. Other things that are formed are sort of pulled out by vacuum, and only cations move towards the magnet. Okay, when a charged particle moves into a magnetic field, there will be a force acted upon that charged particle. This is physics. The charged particle will be deflected by the magnetic field. But it turns out that the degree of deflection corresponds very nicely to the mass of the particle. That is, lighter ions will be deflected more by the magnetic field. Heavier ions will be deflected less. But that's a very linear relationship. And at this point, you're separating your charged particles. You're separating your cations. And once they're separated, they can then hit a detector and register a signal. But the signals will be at different places on your detector, and thus you'll get different signals. Now there's ingenuity built into this. There's calibration. But essentially, we can get a mass spectrum, and the mass spectrum is essentially telling us the mass. It's really telling us the degree of deflection. But the degree of deflection corresponds to the mass. And so it essentially corresponds to the mass. Now, one other thing we can say here is the degree of deflection is also based on the charge. Okay? That is, you can have two particles with the same mass, but one that has a charge of twice as much, like a charge of 2 plus, that particle will be deflected twice as much. So two signals could be the same mass, but they would have different charge. Now, it's most common for anything that we're going to be dealing with here at the introductory stage for the charge to only be +1. Since the charge is always +1, we can essentially call each signal the mass. Okay. By the way, there's other technology in here. There's other physics. For example, these peaks we see here are really signals. The signal really comes from current that's generated by the particle. More particles were apparently hitting the detector here than here, so more current was generated here. We know the relationship between particles and current because in physics you learn something like this equation here, where number of particles per time equals current. I believe this is probably charge. If charge is 1, we can just call that denominator 1, and basically number of particles per time equals current. The more particles, the more current. And so this is essentially how you get your signals. But that's just a little physics application. Okay. We'll take a little bit of reading about what's going on under the hood here, and ultimately how do you get different peaks from your mass spec and why do they correspond to mass. Let's look at an example here at the bottom. Let's say we take this molecule here, it's an ether. Okay, it's got a certain molecular weight. It undergoes electron impact, an ionization method. The molecule is converted to a radical cation. Yeah? The radical cation is often shown very generically, maybe a box or a partial box around the molecule, and then the radical and the charge. Up top I drew the charge first, then the radical. Either way works. This indicates that now it's a radical cation. The mass of this is 122. That's actually the same mass as that because when you lose an electron, your mass doesn't change. Your whole mass, your nominal mass. This is called our molecular ion because it's the entire molecule. The molecular ion can then undergo fragmentation. One type of fragmentation we will learn is called alpha cleavage. It's common with ethers. And this is an example of cleavage. We can cleave off the methyl group, essentially here, and be left with the oxygen CH2. Positive charge on the CH2. We know we have lone pairs here. Okay, we have lost a methyl. That's a mass of 15. We need to learn common masses. A methyl is 15 and ethyl is 29. If we lose 15, 122 minus 15 equals 107. Very often we will say that this is M plus minus 15. We have lost the 15. And this is a common way to describe this because it's quicker. Then you can say, okay, what is m plus minus 15? Well, if it's 122, 122 minus 15 equals 107. And so for this molecule, we would look to have a signal on our mass spec at 122 for the molecular ion, but we would also expect to have a signal at 107 for this cleavage peak, or this fragment. We do not expect to have a peak at 15 because this is not charged, right? As we set up here, neutral fragments will not be seen in the mass spec. Okay. By the way, let's go ahead and point out why this is a good fragment, because we will try to predict fragments. This should be very predictable. One reason this is a good fragment is because it's resonance stabilized. These electrons can move into here, and we can draw a resonance structure that looks like that. This being a CH2 here on the end, right? Carbon with 2 hydrogens, neutral carbon. This is now your major resonance structure, more bonds. This is the primary reason of why the molecule cleave there. And that will be very common. We will often cleave to get cations that are resonance stabilized or stabilized in some other way. One other thing we can note here, just as we said above, when the radical cation, okay, the molecular ion is always a radical cation. When radical cations cleave, what do they form? They form cations and radicals. And indeed, down here, when this radical cation cleaved, it formed a cation and a radical. Very standard type of thing in mass spec when we look at the cleavage. Okay. Let's move forward. Going forward, we will look at representative examples of mass specs. Very similar to what we did with IR. We'll start with this page, which is some alkanes, simple hydrocarbons, saturated hydrocarbon. Let's go. This is hexane, C6H14, a nominal mass of 86. This is the mass spec of hexane. Here at 86, okay, we have M to Z equals 86, because that's 85. 1, 2, 3, 4, 5. 85, and then that's 86, where this peak is. And so this is our molecular ion. Again, this is where this molecule underwent ionization to form the molecular ion. Now let's talk about that briefly. The molecular ion can be formed, and it can survive and hit the detector. Or along the way, it can fragment. And then fragments hit the detector. Usually both occur. Sometimes the molecular ion may not survive. As soon as it's formed, it fragments before it hits the detector. And that's most likely what happened back over here with this compound here. The molecular ion did not survive and never hit the detector. The only thing that hit the detector was the fragments. Okay, what type of fragments do we expect from hexane? Well, this is a a tough molecule to predict fragments. Anywhere you cleave here, it's always going to be a primary cation, not resonance stabilized. For example, first off, the base peak is here. The base peak is what? 1, 2, 3, 4, 5, 6, 7. Base peak equals 57. Okay? M to Z 57. See, here's your x-axis. Well, 57. How could this molecule cleave to give 57? It would have to cleave right here. If it cleaved there, that would give, we could say it gave this cation. One thing I'm not going to show is we're not going to do any mechanism for the cleavage. We know we're dealing with a radical cation. It's going to cleave in a certain spot to give a radical and a cation. Here's a cation we could show. The other portion would be this 2 carbon, and that would be a radical. So we can show cleavage here. Now this guy is 57. You can sort of just be adding that up and say yes, because 4 carbons would be 48, and then there's 3 H's here, 5, 7, 9. 9 H's equals 57. So if you add this cation up, it's 57. This guy, we're really not concerned about it because it's not going to give a peak in the mass spec anyway because it's not charged. Okay, so the base peak came from cleavage here. The fact that this is the base peak tells us that this is the most likely cleavage spot. Majority of your molecular ions cleaved here, and thus you produce the largest amount of these cations, and thus you produce the largest amount of current at 57 to give a peak at 57. But you could also cleave other places. By the way, this is 29. It has to be 29 because these have to add up to the original 86. We could have also called this peak M plus minus 29 because we lost an ethyl. Ethyl is 29. Now, let's look at this peak here. This peak is at 43. All right. 43 means that this lost 43. So I'm calling this M plus minus 43 equals 43. That peak is 43. What could 43 be? Well, what if we cleaved instead here? Call this A. Let's call this B. If we cleave there, we would produce this cation plus that radical. That's 43. This is 43. But only that 43 is going to show up, and indeed it did. What type of cations did we form here? We formed a primary cation and we formed a primary cation. Is there a better cation that we could have formed? The answer in this case is no. In the example below, we will see that we can form a better cation. And in the example below, we will see that the spectrum is kind of cleaner. It's more selective. Before we move down there, what could this peak be here at 29? Importantly, it's certainly not this radical, because neutral radicals don't give peaks in the mass spec. It's most likely just a ethyl cation. That is, we cleaved at the same spot, but mechanistically, the cation was apparently left on this carbon, and radical was left over there. So we would make that cation plus a 4-carbon radical. If cleavage gave us these two, then this would be our M to Z equals 29, and it would register a peak where the neutral radical would not give a peak. Okay, in the end, there's other peaks up here. We could go through and try to give a structure for every one of these peaks, every one of these cations. But just like in IR, we don't need to assign and think about every single peak, particularly those in the fingerprint region of the IR. Ultimately, we need to be able to get some information. What information are we trying to get from the mass spec? Let's move ahead. This alkane has a nominal mass of 114. Do we have a molecular ion? Up here we had a molecular ion of 86. Do we have a molecular ion here? Apparently not. If so, whoever created this mass spec would not have cut off the 114 portion of the x-axis. So apparently there was nothing there. No molecular ion, meaning apparently once this thing became a radical cation, it did not survive long enough to hit the detector as an entire or intact molecule. Where would we expect this guy to cleave? Now this molecule we would expect to cleave here to give cation here as shown plus that radical. Why would we expect to cleave there? Because that's a very nice tertiary cation. Very nice. We can really predict that and expect that to be formed. What is the mass of this? Sometimes you can get the mass by saying, hey, it lost 15. If this loses 15, that would be 99. It might be just as easy to add this up. By the way, if this lost 15, it would make 99. There might be something here. Okay, this is 4 carbons. 4 carbons is going to be 48. That's actually the same mass as that up there. Because now we have 3 H's on here, 3 H's there, 3 H's there, and no H there. That's 9. That's 57. So this is 57. And indeed, it gives a peak at, guess what? Right there, 57. Okay? And that's our base peak. We would expect that to be the base peak because we would expect this thing to cleave to give a nice tertiary cation. It can cleave other places, but those are not as likely. What is this peak at 99? Looks like this lost 15, which is a methyl, CH3. Where would it lose a methyl? Here? No, that would be a primary cation. Most likely place to lose a methyl would also be here. That would give boom, 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 cation here, tertiary, plus we lost the methyl, the CH3 here on the end, but that would be a radical. The radical cation became a radical and a cation once it cleaved. This would be M minus 15, common terminology because this is 15. M minus 15 would be 114 minus 15, so M minus 15 equals 99, and there we go. We do get a peak at 99. So some of the molecular ions cleave there, but most of them cleaved here. Why would this be a better cleavage peak? That's a tertiary cation. I mean, they're both tertiary cations. Why would the molecule prefer to make this one? The answer here is not the tertiary cation. The answer is actually the radical. It's formed and it's still, its stability is still an important consideration. Which is more stable, a primary radical or a methyl radical? This carbon's connected to one other carbon, primary. This carbon's connected to no carbon, so it's not even primary. This would be considered parent. Your primary, first off, your radicals are just like carbocations. They're electron poor. The radical does not have an octet. Radicals are stabilized just like cations. A primary cation would be more stable than just a methyl cation. A primary radical is more stable than a methyl radical. So cleavage took place here to give a tertiary cation, but also a more stable radical. Now, of course, the radical doesn't show up in the mass spec, but it did influence the outcome. Because, I mean, there's a transition state leading to this cleavage. And this transition state is going to be lower because you're forming a more stable radical. The transition state leading to a higher energy radical is going to be higher itself. Okay, in the end, summary for this page is much more predictable cleavage down here because we can anticipate and recognize that we can make a tertiary cation, where up here it's a lot more peaks. Many different primary cations can be formed up there. Okay, let's keep moving ahead. By the way, write your questions down. Okay, let's look at compounds with some halogens in them. This molecule. First thing we need to know here is with bromine or chlorine, these two halogens have common isotopes. Bromine can either be 79 or 81. Okay? And the natural abundance for these two isotopes is about 50-50. Thus, the molecular weight for this compound, you have to use both isotopes, not an average. When you use 79, all this adds up to 122. But when you use 81, all this adds up to 124. So, the molecular ion, which by the way, a lot of times when we write molecular ion, we don't actually show the radical. And we just call it the M+. But it is a radical. It's going to equal both 122 and 124. Now, if you look on the periodic table, the mass of bromine will be like 79.9. We don't use that mass because that's an average mass. That's an average of all isotopes. Whenever we do mass spec, we see individual molecules. So we're going to see both this molecule and this molecule, either 122 or 124. We will never see a peak at 123, at least not as a result of anything with the bromine. Okay. A lot of times this is called M+, and the other is called M plus 2. Now this is where the plus is just a plus sign and the M is just molecule plus 2. Okay, this can undergo mass spec. Do we see 122 and 124? Yes, 122 and 124. So this sample contains both isotopes. And both molecular ions are showing up. Cleavage, pretty clean through here. The base peak is at, what's the base peak? 20, 30, 35, 40, 43. Base peak is at 43. By the way, before we move on, note that these two are in about, very roughly, about a 50-50 ratio. That's what we would expect, because naturally these two isotopes are in about a 50-50 ratio. Now you might have some slight variation due to basically the fine-tuning of the instrument. Peak at 43. Peak at 43, obviously this cannot contain bromine, because bromine is 79 or 81, so bromine must not be present. 43. 43 comes from cleaving off the bromine here and getting this cation plus the bromine radical. Now, there's no bromine here, so we do not expect to see the isotope pattern that we saw with the molecular ion. And by the way, the 50-50 ratio is the isotope pattern of a monobrominated compound. Here, 3 carbons, that would be 12, 24, 36. 3 H's here, 2 there, and 2 here. 7, and that's 43. This has a mass to charge ratio of 43, charge being 1. All right. As we said, typically our charges are always going to be 1. I think there's a problem in the workbook where it asks you to consider something where the charge is more than 1. Okay, we make this cation. This seems to be the most prominent cleavage is right here. It is a primary cation. You know, I reckon this could have cleaved off a hydrogen and made a secondary cation here. That would be just a loss of 1, 121, 123. There actually is a very small amount of 121, 123 here. But it looks like the main cleavage was to give primary cation. Okay. In the end, the isotope pattern that we see here with the bromine is very important here. Down here we have chlorine. Chlorine has 2 major isotopes, 35 and 37. Their natural abundance, though, is 3 to 1, with the 35 being the major isotope. So this molecule, if you add it up, it's going to be 78/80. Again, we see individual molecules. The ratio of these will be 3 to 1. Okay, we can ionize this. We can maybe expect to get a molecular ion in the mass spec. Do we? Yes, right here. We have 78 and 81. 3 to 1 ratio, approximately 3 to 1 ratio. Again, we're not going to get out our ruler, but it should be pretty darn close. These are low res mass specs, so they're going to have a little bit of just inherent error there. So this would be our so-called M+, and this would be our M+2. And the 3 to 1 is called our isotope pattern for chlorine. The other 2 halogens, fluorine and iodine, do not have major isotope patterns. At least not that we're going to be considering. Okay, if we look at this compound here, what type of cleavage is going on? First off, the base peak is the same as above, 43, right? Looks like the same cleavage as above. We cleave here, right? We get this plus the chlorine radical. Halogen radicals are very common. That's probably why it cleaved here, as opposed to maybe cleaving just a hydrogen. Because actually halogen radicals are very common for some reason. If you look at the ozone layer and halogenated compounds forming halogenated or halogen radicals, and then the halogen radicals reacting with the ozone. But down here we also seem to have, again, same molecule, we're just changing the halogen. We seem to have these peaks at 63. But look at this, it looks like a 3-to-1 ratio. This looks like a chlorine isotope pattern, 63-65. That is 78 maybe going to 63, and that's going to 65. 78 to 63, this would be M minus 15. In both cases, these two lost 15 to form these two. Well, what could be 15? Well, this is where we... This is an error here, I believe. Loss of 15 would be, let's call that A. It would have to be here, B. And that would be, boom, boom, this cation plus CH3 radical. That's 15, so this is M minus 15. But since it's chlorine, it's going to, when we add it up, it's either going to be 35 or 37. This should add up to 63 and 65. And so this looks like another way. And what I had drawn here is an error. Because if you add up what I've got drawn there, that does not equal 63 or 65. Two different pathways we're looking at. We could maybe try to look at the rest. For now, though, that should be enough. We'll keep going. Eventually, we'll come back and sort of pull things together. But right now, we're looking at different mass specs and looking at different types of cleavage peaks that are possible, different types of cleavage peaks that are occurring. On this page, importantly, we saw the idea of isotopes. By the way, let's look back over here. Let's look back over here before we move on. Back over here, we had this peak here at 87. 87. Very small, but it's something. What could that be? That is actually a carbon-13 isotope. This is 6 carbons, okay? 6 times 12. What if one of these carbons was a C13? That's actually possible naturally, because carbon is, if you remember from day one, 99% of carbons are 12, but about 1% are C13. So there's a chance of one of these carbons being C13. If 5 of them are 12, 5 times 12 equals 60. And then 1 was 13. That would give your carbons adding up to 73. Then we have 14 hydrogens, and that would give us a total of 87. So, if one of the carbons was a carbon-13, we would get a peak here, and indeed we are. Very small amount. When we first looked at this, we just didn't pay attention to that. But we are seeing the C13 isotope. What's the chance of all these carbons being C13 in a natural sample? Very low. What's the chance of 2 of them being? Actually reasonable. If 2 of these were C13, then this would add up to 88. Well, we don't see any 88, but maybe the instrument is just not sensitive to pick it up. I guarantee you, in hexane, there's at least a few molecules where 2 of the carbons are both C13. Okay. Let's look here at another compound. Now this is an ether. Yeah. Molecular weight is 74. That's a nominal mass. We're not considering any carbon isotopes. Do we have a 74? Yes. So we have our M+, molecular ion that survived long enough to hit the detector and registered a peak. The rest would be fragments of this. At this point, we're going to start cleaving in a very predictable place, and we're going to call it alpha cleavage. This molecular ion, or radical cation, is going to cleave here to give, let's go this way, boom, boom, oxygen, cation here, plus a CH3 radical. All right. Could have just drawn that here. This and this is the same thing. This is going to have a mass to charge ratio equals, well, it's M minus 15, because that's 15. 74 minus 15 would be 59. Do we have a peak at 59? Yes, right here's our peak. That's 59. Yeah. It's a very predictable peak, because this is resonance stabilized, and this is just like the one we saw at the bottom of the page that had the instrument description on it. We can do resonance structure here, resonance arrow, and we can boom, boom. It looks nearly exact same as we saw before. So resonance stabilized cation, and that's why it's a good place to cleave there. And going forward, we will be looking to form resonance stabilized cations. In the previous examples, we didn't have any resonance. All we had was looking at possibly primary, secondary, tertiary nature of the cation. What is the base peak? The base peak is 31. What could 31 be? Actually, I'm not quite sure what 31 is, and that's kind of odd here. I mean, the only other place to cleave here would be here. But if you cleave there, this is not going to be good, because you would have maybe a cation on oxygen and a radical there. That oxygen doesn't have an octet. As we said in class, that's just not a good place to cleave. Also, neither one of these equals 31. In the end, here we go, summary. The peak at 59 is what we really need to predict here. The peak at 31 in this example, it's quite odd. And I'm not able to give you a structure for that. It may be the so-called grand order peak, where, for example, maybe this undergoes some type of cleavage or rearrangement, and then to give a smaller fragment. Ultimately, it seems like it's one carbon, one oxygen, and maybe a couple of hydrogens. But I'm not. It's hard to get that from a simple cleavage of the original molecule. Okay, but we can predict this. Compound below. First off, this is the first molecular weight that we've seen that's odd. But that's to be expected because of the so-called nitrogen rule. If a compound has an odd number of nitrogens, the molecular weight will be odd. If the compound has an even number of nitrogens, or zero being an even number in this case, the molecular weight will be even. For example, up here, no nitrogens. We consider that an even number. Thus, it's an even molecular weight. One nitrogen, odd molecular weight. Okay, you add this up, the mass of this is 101. Do we have a 101 in the mass spec? It's possibly there, it's mostly absent. That means that the compound did not survive long enough to hit the detector. I'm going to have to power up a little bit here. Okay, so molecular ion mostly absent. What type of cleavage peaks do we have? We have this peak at 1, 2, 3, 4, 44. By the way, this is our first major peak that we've been looking at that has an even molecular weight. That goes again with the nitrogen rule. Above, no nitrogens, odd molecular weight, even molecular weight. All the cleaved cations were odd. On the other hand, if you have an odd number of nitrogens, your original molecular weight will be odd, but all of your cleaved cations will be even. Okay, I've already given you the structure here, but basically where can we cleave to give a resonance stabilized cation? We can cleave right here. That would give cation here, and then we could show the radical there. Now mass, that's a huge, I think that's probably 57. A butyl is 57. That means this is M minus 57. That's such a huge number, I think that's right. 101 minus 57, that's got to equal 44. And indeed it does, and that's why our peak is registering at 44. Why is this a good place to cleave? Well, it's resonance stabilized. And we can draw a resonance structure as such, and because the cation is resonance delocalized, it's resonance stabilized, this is a predominant cleavage pathway, and that's why there was so much current registered at the position of 44 on the detector. Could we have predicted another cleavage here? What if this had cleaved in the same spot, but mechanistically the cation was left on the other carbon? And we have gotten that plus this radical. Again, we're not looking at any mechanisms. We're just saying radical cation can cleave to make one radical and one cation. Then we have the charge and the radical on the two atoms that were just separated. But we could do it this way. This would be 57, same as that. Okay, the presence of an electron here doesn't change the nominal mass, and this would not be observed. Do we have any 57? Very small amount. Very small amount. It's a reasonable cation, tertiary. But apparently the molecule preferred to cleave this way. So much more particles hit the detector and cause more current here. Bigger signal. Is there another potential cleavage that might be reasonable and we could argue had some stability? What if we cleaved here? And put cation there plus a methyl radical. This would be M minus 15 because we just lost 15. 101 minus 15 should be 86. Should be 86. Do we have 86? Ah, we do. So we can maybe predict a structure for the 86 here. Seems reasonable, tertiary. Why was this route better than this route? I mean, they were both tertiary. It's a little bit counterintuitive. This radical looks better. It sort of looks better to me. Not going to go into it. But for some reason it chose this way. Hard to know sometimes. In the end, the resonance stabilized cation is the one we would predict, and indeed that's the major pathway. Now, I don't think we've used a term yet. This is called alpha cleavage. Whenever we make, alpha cleavage. It's an example of alpha cleavage. This is an example up here of alpha cleavage. Whenever we make cation next to a lone pair, that's alpha cleavage. Now it can be next to a pi bond as well. Typically whenever we make a resonance stabilized cation, it's going to be called alpha cleavage. The alpha comes from, if we look up here, it's really shortened for alpha beta cleavage. We're really cleaving between the first atom and the second atom after the functional group. Okay, first one's called alpha, next one's beta, and we cleave between them. But we just quote the alpha, sort of like when we quote the positioning of an alkene. We just quote the first number in the nomenclature. Down here, here's their functional group. The first carbon's alpha, the next one's beta. We cleaved here to give this cation. That's an example of alpha cleavage because cleaving there gives a resonance stabilized cation. I will more commonly say alpha cleavage is where you cleave to make a cation next to a lone pair. Cation next to a lone pair, because that makes it resonance stabilized. Okay, over here we're going to bring in pi bonds because we know we can do resonance with pi bonds as well. Benzene compound, molecular weight of this is 20. Add it up. You won't get 20. You'll get 120. 120. Best place for this to cleave? It's right here. That will give this cation plus a ethyl radical. And this cation is a benzylic cation. And we saw benzylic cations in class. Okay, resonance stabilized. Look back at your benzylic cation with your resonance structures of this in class. This can be called alpha cleavage if you consider the benzene ring sort of the business end that's going to be helping you here. We cleave between the first and the second carbon. Benzylic cations, commonly seen in mass spec, where we form cations, right? But we form good cations when possible, and the benzylic cation is a very good cation. Okay, look at the compound below though. These are constitutional isomers. Same formula, different connectivity. All right? Up here, we cleave between the benzylic carbon and the next carbon. Okay? Two benzylic carbons. This is a CH3. That's a benzylic carbon. That's a benzylic carbon. But only this one has a carbon connected to it that we can cleave. We're going to cleave here. That's going to give this plus what? A CH3 radical. This cation is M minus 15 because we just lost the 15 radical, which is 120 minus 15, 105. Okay? Do we have a 105? Yes, it's our base peak. Okay? 105, base peak. Where up here, we didn't predict a 105. We predicted a, what did we lose? We lost 29. 120 minus 29 is 91. We predicted 91 here, and indeed, we have a base peak of 91. That's what we would predict. The only way for us to get 91 down here is for us to cleave. Okay? To cleave off the ring and to make methyl here. I'll just draw it as a line bond. To make a cation right on the ring. This would be 91. Problem is, this is a very bad cation. Beginning students think that this is resonance stabilized because it's so close to these pi bonds. This cation is not resonance stabilized. No resonance. Try to draw a resonance structure of that. It is not. You have 6 p orbitals here all lined up. The new p orbital here is going to be perpendicular to the other 6. That is a single p orbital that is not overlapping with anything. On the other hand, here you have these 6 p orbitals, and then that 7th one can line up with these 6, and you have conjugation here, and you can show resonance structures here. In the end, we would predict 105 here, and we only predict 91 up here. So, the two constitutional isomers can be readily distinguished by mass spec because one mass spec has 91, the other mass spec has 105 as base peaks. Pretty clean otherwise. I mean, some minor fragmentation, but this is going to give us an answer right here, most likely. Okay. Maybe with that one, with that example, we can go back to the beginning now and make comparison of the earlier, at the very beginning, when we looked at the IRs of the two alcohols. Here are the IRs of the mass specs. IRs of the mass specs. Okay. These would be the mass specs of the two compounds. compound. Where do we expect to cleave? I would expect to cleave here to give this radical plus this cation. I would call that alpha cleavage because it's between the first and second carbon from the functional group. Why is this good? I can do resonance here, and I can get this here. This would be 29, so this should be M minus 29. Yeah? The mass is 60, so 60 minus 29 should be 31. Right, we expect to peak at 31, and indeed we do. It's a base peak. So we expect to peak at 31. We look and see, okay, which mass spectrum has a peak at 31, and there it is. On the other hand, down here, there's actually two different alpha cleavages we can do. We can cleave here, call that A, and if we cleaved at A, we would get actually that plus a CH3 radical. That means this would be M minus 15. 74 minus 15 equals 59. And indeed, we have a peak at 59. But we can also do an alpha cleavage on the other side and call that B. That would give this plus an ethyl radical. We cleaved off the ethyl. That's 29. So M minus 29 would be 74 minus 30 would be 44. Add 1 would be 45. And indeed, we have a peak at 45. So, before we even look at the mass spec, we know we expect peaks at 45 and 59 for this molecule, where for this molecule we expect to peak at 31. Then we can just look at the mass specs and we can tell which is which. Where over here, we know what we expect for both of these in the IR. The problem is, both IRs show that, and we have nothing else to help us distinguish. IR has limitations. Most of your analytical techniques are complementary. IRs give you an idea of functional groups. Mass spec gives you an idea first of mass, but it also gives you an idea of how things are connected, the backbone. Because by knowing what we expect, we can sort of see what cleavages occurred, and that really is telling us about how the backbone is put together. The fact that both of these are alcohols is really not a major part of mass spec. Okay, let's move forward a little bit more. Let's talk about carbonyl compounds. We can also do alpha cleavage with carbonyl compounds. The alpha beta cleavage, though, is from the oxygen. And a common place to cleave is here. This is going to give this plus a CH3 radical. This cation, it looks a little funny because it's double bonded, but it's resonance stabilized. These electrons can move in here, and we can get, now I'm going to draw this carbon here. That's the original carbonyl carbon. It now triple bonded to the oxygen, one lone pair left, right? That's what all this means is, one lone pair left. And then we have boom, boom, boom. Now though the plus charge is on oxygen. Looks a little funny, it's now triple bonded. This ion here, remember the true structure is a hybrid, this is one ion. This is called an acylium ion. A-C-Y-L-I-U-M. All right. There's your acylium ion. You might draw the hybrid, which is major. This is major. This is the minor resonance structure. The hybrid's going to look more like this because there's more bonds. More of the positive charge here is on oxygen, really. So, it's our first look at acylium ions. They're commonly formed in mass spec. You will form them in reaction mechanisms in organic 2. In organic 2, when you hear acylium ions, remember them from mass spec. Okay, we lost 15, so this should be M minus 15. Molecular weight is 86. 86 minus 15 should be what? 71? And indeed, we have a peak at 71 for that acylium ion. Now, there's another way to get an acylium ion here. We could cleave on the other side, call that A. We can also do a B cleavage. That would put cation here, another acylium plus boom, boom, plus that radical, a 3-carbon radical. Now this is pretty big, but that is 43. 3 carbons is 36, and 7, 43, yes. So this is M minus 43, which equals 43. And indeed we have a peak at 43, which is for this acylium ion. 2 different acylium ions that could be formed here. You should be able to draw a resonance structure of this acylium ion. We know that this is the major resonance structure of the acylium ion, right? Very important to know the structure of this ion. Okay. Why was this such a more predominant cleavage pathway? Both of them are resonance stabilized acylium ions. But let's look at the radicals. Which radical is better? Primary radical or methyl radical? Primary radical is better. Thus, the system favored coming here, and that's an argument for why the base peak is at 43 and not at 71. Okay, McLafferty. Another way that carbonyl compounds can cleave is the so-called McLafferty rearrangement. The McLafferty rearrangement gives a radical cation. All right? Of course, anytime we cleave, we're cleaving a radical cation. Okay? That had to happen first. Then we can start cleaving. The McLafferty is where the radical cation is still a radical cation. What this means is it ejected a neutral molecule. It cleaved off a neutral molecule and remained a radical cation. Now, I'm not going to cover the McLafferty here. I want you to look up the McLafferty rearrangement in your textbook and cover that yourself. And it is typically included. There's questions about this in an upcoming lab report, and I want you to cover that yourself. Because it's very important for you to learn how to use your textbook and to answer and to find information on your own. And so I expect you to look at this on your own. One thing you'll see is typically when the cleavage takes place, the fragment here is in an enol form. Then this can, of course, undergo tautomerization, and the keto form may be shown in your textbook. But there is sort of a cyclic transition state here. Okay, so look at that on your own. One thing we can state that is the McLafferty does require a gamma hydrogen. Alpha, beta, gamma. It requires a hydrogen on the 3rd carbon from the carbonyl. 1, 2, 3. Okay, it's a gamma carbon. There are hydrogens there. You can do the McLafferty because of that. Down here, there's not even a gamma carbon. Alpha, beta, either way. You cannot do McLafferty on this compound. Okay. One last thing about McLafferty. Note that there's no nitrogen. Molecular weight is even. Ions are odd. But note that the McLafferty adduct or product after the cleavage is 58. Okay, it's even, just like the original radical cation. Even, where your plain cations that are formed are odd. Okay, let's look down below. This ketone is symmetrical. That is, if we cleave on this side, it's going to be the same as if we cleaved on the other side. And if we cleave here, we get this plus, we lost 2 carbon. This would be 29. Should be M minus 29. Loss of 29, which should equal 86 minus 29 should be 57. That's what we would predict. We predict this. Do we have a peak at 57? Yes, right here. It's actually our base peak. So our prediction leads to a base peak. Very nice example here. We also have a peak at 29. What could that be? I would have to say that that's where we cleave at the same spot, but for some reason the cation formed on that carbon and left the radical there, and then this is 29 because it's a cation, it showed up. I would not expect that to be as tall. Of course, there's often things we see in mass spec that we might not really expect. It's a high energy process. This is what we predict. I'm surprised that that peak is as tall. That cation's not stabilized. This may have some stability here, but that's unexpected. Typically we want to predict with carbonyl compounds acylium ions. Acylium ions. There's no McLafferty here, but again, because there's no gamma hydrogen. So once you learn about that, you can see and confirm that there's not one here. It's going to be hard to confirm because you can't even hardly predict one. Okay, that's really the most common compounds. We've got carbonyl compounds. We have benzylic cations. We have these cations next to a lone pair, either like ethers or amines. We have isotope considerations. Back at the very original, we had cations next to oxygen lone pairs of an alcohol. We went back and we went through that. Let's make our way home here. Okay, next page. This is homework. All right. We have 3 compounds and 3 mass specs. Assign each compound to its correct mass spec. All right. Type of problem you may see. You should also look in the workbook for other problems. They'll be very similar to the IR. There'll be a list of compounds, there'll be lists of mass specs, and you assign each compound to a mass spec. Or if there's 10 compounds, you just assign each mass spec to a compound. Okay, how you want to do this? I recommend you start by looking at a compound and saying, okay, what do I expect here? What do I expect? For example, you might expect to cleave here to make cation there next to a lone pair. All right. Draw that fragment, give it a mass. Do you expect any cleavage any other places? If so, draw that fragment and give that mass. So maybe this has, 2 or 3 masses that you predict. Write those down. Do it again for here. Write down the masses of the fragments that you predict. Write down the masses of the fragments. Have that. Only after you do that, then you look over here and say, okay. Now this came from a textbook, and they were nice enough to sort of give you numbers which make you sort of focus in on that. Base peak of 73, base peak of 59, base peak of 45. No 45, small 45. Back over here, did you predict a fragment of 45 for any of these? If you did, it's most likely going to belong to this mass spec. By the way, what's the mass of these? If each of these had different masses, we don't even have to look at fragments. This brings us to recognizing molecular ions. The molecular ion is typically going to be the peak of highest mass, but you may also have isotopes. And ultimately, well, there's no tick marks here, but if you add these up, I think they're all 88. 88, 88, 88. Okay? I'll let you go from there. This is just an example from a textbook. Examples of alpha cleavage. They're showing the resonance stabilized. Okay? They're not showing the original carbocation. They're only showing the major resonance structure. Yeah? Okay. Couple of miscellaneous things. Very important though. This sheet shows an example of GC mass spec. Very often mass spec is combined with gas chromatography. It's a combined analytical technique where the gas chromatography is done first. You may or may not have a pure compound. The gas chromatography will first separate components in a mixture. Then each component is then sent to the mass spec and you register a mass spectrum. This is a product from a reaction that was done in the student research lab. We had a product that was extracted from the reaction. We did a GC mass spec of that product. Is it pure? Or is it multiple components? This is the GC part. Okay? The GC, just like TLC, gives a peak for each component. Now this is actually solvent. But we end up with 1, 2, 3, 4 peaks in the GC. This would be analogous to having 4 spots on your TLC. Now, the GC, you're going to be able to quantify your components much better. Now, I'm not going to go into that here, but ultimately, this peak, the area under the curve, is much larger than the other 3. And this is your major component, then this one, and it ends up that progressed back. Your first one was a more minor component, but it's still present. And each of these had a different retention factor, or RF, on the GC column. Now, when this comes off the GC column, it goes to the mass spec as a single component. These are labeled A, B, C, and these are the mass specs of each of these peaks. For some reason, I'm not sure why we did not get a mass spec of this one, which would have been D. This is the mass spec of here, here, here. Molecular ions here of 293, 255, and 237. Looking at molecular ions, we were able to tell that this was this molecule. This was actually the starting material of our reaction. What we were doing, we were trying to fluorinate this ring. We did the reaction. The product mixture still predominantly showed starting material, but the reaction mixture also showed presence of a monofluorinated compound, which would have a mass of 255. It also showed presence, unexpectedly, of 3 fluorines, which was a mass of 293. Now, what did we see first? We first saw 293, and then we're like, well, how do you get a mass of 293 from this molecule? Well, if you think about it, if you add not 1 fluorine but 3, the mass will then equal 293 in this manner. And then from knowing some chemistry, we proposed this structure, but this structure would have to be proven by other ways. We really didn't look at the cleavage here. Really didn't need to. This is the reaction we did, and the GC mass spec really helped us to see that it was 4 components. I'm not sure we ever figured out what that very minor component was, but having the mass is very helpful. Okay, that's G. But that was a mixture, not pure. The next page I show you a GC mass spec of a pure compound. Just like TLC, if you have a pure compound, you expect 1 peak in the GC. All right. Then we can get a mass spec of this. The mass of this is 337, and you see the mass spec shows a molecular ion of 337. This is probably some carbon-13 isotope. And 337 is good evidence that we have this molecule. We could then get other evidence. Again, you like to have multiple pieces of evidence to prove a structure. There we go. While we're here, if you take advanced courses, you may run GC mass spec yourself. Parameters are very important. For example, flow rate on the column. Particularly here, I'll point this out. This is the GC portion is in an oven. It's heated, and you can vary the temperature. In this particular run, it started at 200 degrees. It stayed there for 5 minutes. Okay. Then it ramped up to 275. It ramped at 45 degrees per minute. So it came up to 275. It took about 2 minutes or less to get to there. And then it stayed at 275 for 15 minutes for a total run time of about probably 20 to 25 minutes, including the ramp time. Just over 20 minutes. And indeed, if you look at this here, this is your time on the column, and you see it's just over 20 minutes that the GC ran. But the compound of interest came out with a retention time of about 9 minutes. Okay. Basically, things are separated on the column, and then this is connected to the mass spec. What you don't want to do is get a mass spec of a mixture, because it will be incredibly difficult to interpret. You'd rather have a mass spec of a single pure compound, and the GC column helps ensure that. Okay, last thing, high resolution mass spec. This is where you use 4 decimal places. For example, answer the following questions. A standard low resolution mass spec of an unknown compound gives a molecular ion peak of 84. Low res, nominal mass. Which of the above compounds is the unknown? The problem is, all 3 of these compounds have a nominal mass of 84. If you look at it, add it up. So this 84 does not give you an answer. What if we get a little bit better resolution and we can get 84.1? Well, it still doesn't give you an answer, because if you round this off, that's 84.1, that's 84.1, that's 84.1. They're all three still 84.1. On the other hand, if we get a very sophisticated instrument with very high precision, known as a high resolution mass spec, which is going to cost us some money, when we do the mass spec, we may get a molecular ion of 84.0571. If we do, that gives us some pretty good evidence that the answer is here. We have that molecule. Because now we're taking this out to 4 decimal places, and if you take this mass out to 4 decimal places, you see we have similarity here. Much closer here than it is to the other two. So only by high resolution mass spec can we distinguish these three, really. Now, of course, these three could be distinguished by IR or other means. But in terms of mass spec, they can only be distinguished if you use a high resolution mass spec. Now, when you're adding these up, instead of using 12, if we used carbon 12, we could get 84. You'd have to use 4 decimal places, and you can find tables like this. And so, of course, 12 by definition is 12.0000. But, for example, nitrogen, if you stick to common isotopes, more than 14, but it would be 0.0031. And you would use such a number. So, go figure. Okay, this is interesting. In the past 10 or 20 years, instead of only injecting solutions into a mass spec instrument, we now have sort of so-called direct analysis, and this is a picture of just holding a pill up to the mass spec port, and molecules are pulled off of the pill, and we can get mass spec here. 2002 Nobel Prize for better ionization methods. And in the end, want to get a job. They're looking to hire someone to do mass spec at this drug company. This is over 10 years old now, but such ads appear routinely. Drug companies very much value people who can use instrumentation to support drug discovery efforts. Okay, so that's the mass spec video. Please write down your questions, and please start working problems in your textbook, reading your textbook, and supplementing this information. And we will at some point look back at this one problem here. Okay guys, that's mass spec.